everyone, this is Dr. Daya Sagar Chowdary, Senapati, Assistant Professor, Department of Electronics and Communication Engineering, Aditya University, Surampalem. Today we would like to discuss about the topic combinational logic circuits. So these are the contents that are included in the combinational logic circuits. We call simply that one as a combinational circuits. So the contents are half adder, full adder, half subtractor, full subtractor, decoder, encoder, multiplexer, demultiplexer, also the comparator. So these are the major block diagrams and contains circuits also inside the combinational logic circuits. Now learning outcome. So at the end of this lecture, students will be able to know about the adders and subtractor circuit to calculate 2 or more bit combination. So combinational logic circuit. So what is combinational logic circuit? These produces outputs based on current inputs with no memory or past data. That means we can also represent this figure. Let us assume this figure. So this figure contains a block diagram. So that is combinational circuit. So it is having inputs. That means we are using here the A, B, C, so on up to N. These are the inputs, and outputs are A bar, B bar, C bar, so on up to M. That means it contains random inputs and random outputs. That means we will expect outputs like this circuit is like open loop circuit. So we apply the inputs, at the same time we will get the outputs. This is the only common for the combinational circuits, and fundamental in digital design for processing and decision making. So most of the time here we are using this combinational circuits as an adders and subtractors, that is for calculation part, and for encoders, decoder, multiplexing and demultiplexing concepts we use for decision making. So this is the fundamental basic block diagrams for this particular operations. And coming to the examples, binary addition and subtraction, this is for calculation or processing for the purpose, and half adder, full adder also we will discuss in this particular lecture, and multiplexer and demultiplexer, this is for decision making, and encoders and decoders are we are simply for processing the data from mostly we will use this particular combinational circuits in the CPU to RAM and ROM. Likewise we use inside or in between these two devices. So this is the combinational circuit. What are the features and what are the circuits that we are used inside that one? So this is the definition. So circuits whose output depends only on the current input. So present we are applying the current input and we will take the output at present. That means the output doesn't depends on the past inputs. So we will get the inputs and outputs at accuracy. And memory, no memory. So no feedbacks loops are there. So that is why no memory is included. So if memory is included means we call that one circuits as a sequential circuits, but here we are using the combinational logic circuits. So for combinational logic circuits there is no memory elements. Output depends solely on the present input values. So we already discussed it in the previous line. Examples: adders, multiplexers, encoders, decoders, ALU, which is nothing but arithmetic logic unit. It is also depends on the present input and present output only. Timing, instantaneous output change as input changes. You know, first of all, if you change the inputs also, we will get the outputs for the particular input only. Whatever we changed the input, we get the changed output only. State, no internal state, output is purely a function of inputs. Simply output is a function of inputs only. And complexity, generally these are simpler and faster in terms of design because no feedback loop is there. So that is why it will give the faster outputs when compared to the other devices. Other devices means that is the sequential elements, sequential devices. Sequential devices contains the memory element. So those devices contain the feedback loop. That is why these combinational circuits is not using that feedback loop. That is why we simply take the outputs as a direct outputs from the whatever we are applying the inputs. This is the complexity. That is, complexity is very simple. And speed, faster, because no loop is there. That is why this is faster, because they don't have required clocking and memory. So that is one of the best example, because if there is no clock means these devices will work fast. So coming to the combinational circuits, so combinational circuit consists of input variables, logic gates and output variables. So these are the major terms that we have to use inside that combinational circuits. So that means inputs, whatever the inputs we have to give to the block, so that is the input is required, and logic gates, because the block, we are talking about the block, so that block contains all the logic gates, and finally we will get the output. So that output is nothing but we will assign some output variables. This is the output variable concept. The n input binary variables come from an external source. The m output variables are produced by the intent combinational logic circuit and go to an external destination. So depending, we cannot expect, that means, so for encoder number of inputs is different, and for decoder and number of inputs is different, and outputs are different. So depending on the circuit only we can analyze whatever the inputs and whatever the outputs here. Also that is why here the representation is here n input binary variables and m output binary variables. So depending on the circuit only we can predict that this circuit is of having this much of inputs and outputs, and that circuit is having this much of inputs and that outputs, like that we will consider. Now, so for n input variables there are 2 to the power of n possible binary combinations. The combinational circuit is specified with a truth table that lists output variables. See, here we can observe that the block diagram. So that is a combinational circuit. So it is having n inputs and m outputs. So we cannot expect this particular block diagram because this is a combinational circuit block diagram. So maybe the inputs are n and maybe the outputs are m. But depending on if it is decoder, so definitely we know that that n into 2 to the power of n. That is the n is the inputs and 2 to the power of n is the outputs. So depending on this block diagram, that is decoder, we can predict the number of bits in the n side, that is input side, and at the output side. But if it is a combinational circuit, because combinational circuits are of adders, subtractors, decoders, encoders, like multiplexer, demultiplexer, and also comparators. So we cannot predict the inputs and outputs. That is why we will keep this one as n inputs and m outputs. Now, the first one we have to go to the adders. So before going to the adders are of two types. One is half adder and other one is full adder. So for half adder, it contains only two inputs. That is, here I am taking that x and y are the inputs, two inputs, and the outputs that are produced by these two inputs are, as usual, adder means summing. So summing means the sum. From our childhood, we are simply what we call that one as a carry. So if the sum is more than 9, then definitely we have to use that tens position number to the tens position number. So that means 9 plus 9, let us take this example, 9 plus 9, that is 18. We know 18. So that means we have to keep that 8 as in units place, and the 1 is the carry now. So that 1 we have to carry here. If it is 0, the tens position of this particular 9 is 0, and also for this particular 9 is tens position of this 9 is also 0. Then this carry we have to add to this 0, and the result is again added to this 0, and finally we will get the output as 1. So this we call it as a carry. So here in digital circuits also we have to take care of this carry, both sum and carry. That is why we included this sum and carry as a S and C. So here x is the input and y is the output. Here if it is the sum, we have to perform the sum, that is S. We represent it with S, and the carry, whatever we are getting the carry. So here simply we are transferring the carry to here, that is C. So this is the half adder. Half adder contains two inputs and two outputs. Now coming to the truth table. So for any circuit we have to observe the truth table for verification part. So here we are taking the two inputs. That means 2 input contains 2 to the power of n, that is 2 to the power of 2, that is 4 combinations. So 4 combinations, either that both are in 0, both are in 1, either one is 0 and one is 1, and other one is 1 and other one is 0. So likewise these 4 combinations we are observed here. Now for this particular operation, so 0 plus 0, so here we have to add these two inputs. That is why 0 plus 0, that is 0, sum is 0 and carry is also 0, because no carry we are carrying to tens place. Here 1 plus 0, that is again sum is 1 and carry, there is no carry, that is why it is 0. And 1 plus 0, again here sum is the 1 and carry is, there is no carry, we are not taking any carry, that is why the carry is 0. While coming to the 1 plus 1 combination, so the sum is 0 and the carry is 1. That means, see, here we are using only 0 and 1. That means, so 0 and 1 is, that is okay. So 0 and 1, we have to repeat that 0, 1 and we have to produce the number 2. So in binary, we know that 0, 1, that is 1, 0, that is 1, 0 is the representation for 2. That means 1 plus 1, we know already in decimal, that is 2. But while coming to the binary, that is 1, 0. So binary 1, 0 means sum we have to give, that is 0, and the carry, whatever we are getting, the 1 is the carry, and we have to transfer this 1 to the next position, that is tens position. So it will carry. So that is why this truth table is like this. And if we observe the C and S, that is carry and sum, we have to draw a circuit. From this truth table, you have to draw a circuit. So how we can draw is simply by taking the K-map circuits, K-map table, then only you will come to know the equation, and with the representation of the equation, then we can easily construct the circuit diagram. So if we anyway, for half adder it is easy, because the entire truth table just looks like an XOR gate. That is why the representation is XOR gate. And while coming to the carry, it is simply looks like an AND gate. So for 1, 1, this is 1. So that is why it looks like an AND gate. That is why we can use this one as a AND gate for carry. That means we will get the sum and carry for X and Y inputs. That is the simple representation of the circuit for this particular half adder block diagram. Now for 3 bits, because we are also having the carry, that is third input, concentrate on the third input also. So that is why here I am also taking the 3 inputs, that is what we call this one as a full adder. For full adder, it contains 3 inputs and the same outputs are carry and sum again. So XY is the inputs, and finally let us consider this Z as the carry, whatever we are carrying. There 9 plus 9 is 18. So here the 1 is the carry, so we have to don't forget to present this carry, because this carry is also plays a vital role in the addition subtraction. So that is why we are using this carry. So if carry is there, definitely the inputs are 3. So that means if it is 19 plus 19 means definitely this is the first input, this is the second input, carry is the third input. That is why full adder contains 3 inputs. Directly we can add these 3 ones, 1 plus 1, so that is 2, 1 plus 1, that is 2. So that means here 1 plus 1, that is 2, 2 plus 1 is 3. So finally the output is 38. So that means 19 plus 19 is 38. So we know that from our childhood, but coming to the digital, we have to use this particular carry and sum. So that is why the third input is the carry. So for that example, we are taking the third input as the carry, and sum and carry is same for both half adder and subtractor, sorry, so full adder. So X, Y, Z, so sum is there, and if the carry is there, so we have to carry it to next. That means this is if we consider this one as a units place, this one as a tens place. Likewise, we have to send that carry. And this is the truth table for the full adder circuit. So again, it contains 3 inputs. So with the help of 3 inputs, so we can produce 2 to the power of 3, that is total 8 combinations. So we already represented this as 8 combinations, 0, 0, 0, 2, 1, 1, 1, and finally according to the addition, we have to follow the summation and carry. So here 0 plus 0 plus 0. So we know that sum and carry are zeros. 0 plus 0 plus 1. So 0 plus 0 is 0. 0 plus 0 is, sorry, 0 plus 1 is 1. So the sum is 1, carry is 0. Here in this combination, 0 plus 1 is 1, sum is 1 and carry is 0, and 1 plus 0 is sum is 1 and carry is 0. So simple. This represents, we can easily represent. Here 0 plus 1 is the sum is 1 and the carry is 0. Now the sum is 1, right? So 1 plus 1, so the sum is 0, now the carry is 1. So this is also represented like this. Now 1 plus 0, the sum is 1 and the carry is 0. Sum is there, sum is 1. So 1 plus 0, here sum is 1. So 1 plus 0, that is sum is 1 and the carry is 0. Here 1 plus 0, so 1 plus 0 is the sum is 1 and the carry is 0. Sum 1 is there, right? So 1 plus 1, so the sum is 0 and the carry is 1. So likewise we have to represent. And here 1 plus 1, so the sum is 0 and the carry is 1. Now sum is 0. So 0 with 0. So 0 plus 0, that is sum is 0. But don't forget to note down that carry. That is why this carry we have to represent here. So that is your carry as 1. Here 1 plus 1, that is sum is 0 and the carry is 1. So don't neglect this carry. Now 0 plus 1, so that sum is 1 we know, but don't neglect this carry. So this carry is simply coming to here. So that means sum is 1 and carry is 1 for both, for all the 3 1 as an input. So this is the two table representation. So the next is we have to construct the circuit diagrams. So for circuit diagrams we have to use the K maps, Karnaugh maps, we already know. So K maps for S and for C. So this is the sum part K map. So totally 8 combinations. That is why we are using the total 8 blocks, and for with the representation of 0 0 0. So 0 0 0 1. So where the ones are there, we have to represent the corresponding combination inputs. Here this is the corresponding combination input. There we have to keep 1. Here also 1 is there. So the corresponding inputs we have to take the 1. Likewise we have to take all the ones, and if we calculate the particular equation, or if we calculate the particular equation with the help of this K map, then we will get this equation. So likewise if we again calculate or take the common terms, then we will get the x bar, x, y, z. There is a relationship between these x and y and z. So that is the simple XOR gate. That means XOR x, XOR y, XOR z. So this is the simple representation for the particular equation whatever we are getting from the K map. And also we have to use the K map for the carry also. So again the same combination. So for ones we have to take care of the particular inputs. Here 0 1 1. So 0 1 1, this is the combination. So here 1 we have to place. Likewise here 1, here 1, here 1, because it contains 4 ones. This 1, 2, 3, 4. These 4 ones we have to represent here. Now according to this calculation for carry, xy plus yz plus zx. So this is the representation. Just this is the cyclic representation for the carry for the full adder circuit. So this is a simple full adder circuit which contains 2-bit input plus carry. So here it is a simple circuit. So inside the box this is the circuit, and outside we will get only the terminals. That means this complete block diagram acts as an IC. Let us take this one as an integrated circuit. So this entire block is like a IC design, and internal blocks are like simple logic designs. That means every IC contains internally only the logical elements, that is logic gates only. Here this is the simple representation for both input, that means x, y, z are the inputs, and s and c, sum and carry, are the outputs. So those 2 outputs are coming out from this block diagram, and 3 inputs are moving inside the block diagram. So finally you will get the full adder circuit outputs here. So the same equation represent here, that is s is equal to XOR x, XOR y, XOR z, and c is equal to xy plus yz plus zx. So this is the representation of sum and carry for the full adder circuit. So mostly we will use this full adder and half adder for calculation part, that is summing part in the computers actually. So these are some applications that we are using this full adders and half adders inside the IC designing or computers or mobiles or any electronic gadgets. Here full adders are used in ALUs, that is what we are discussing about, ALUs of CPU or CPUs of computers, because calculation part is very important in the ALU. That is why we are using the full adder circuits in the ALU. And for calculators, because for calculation part, calculators is the device, calculator is the device we have to use. So definitely in calculators we are using this full adder circuits. Full adders also help in carrying out multiplication of binary numbers. So we know already multiplication is just like a repetition of the summing part. So 2 into 3 means 2 times we are using the 3. So 3 plus 3, that is 6, we know. So 2 times the 3. So likewise in multiplication also these full adders will play a vital role. And full adders are also used to realize digital circuits like multiplexer, big block diagram. Inside the big block diagram again we are using this full adder circuits. And full adders are used to generate memory addresses. Also this is used for memory addresses to generate. Full adders are also used to generate program counter points. So programming counter points also we are using this full adder circuits. Also these are used in GPUs, graphical processing unit. We know already because graphical processing is an alternative for the ALUs nowadays. Coming to the full adder circuit, so we can construct a full adder circuit with the help of two half adder circuits. So this is the design, or this is the block diagram for the full adder circuit using two half adder circuits. So here for a half adder circuit contains two inputs. So the output of the, that is sum, is given to the one input terminal for the half adder circuit, and the third, whatever we are applying, the third input is given to the second input for the half adder circuit. Finally we will get the sum, and the carry, both the carries, if we apply both the carries to the OR gate, we will get the carry. So likewise this simple construction for using two half adders to construct a full adder circuit. So this is again the same equations, nothing else is there. So sum is x XOR y XOR z, c is equal to xy plus xz plus yz. This is the combination, and if we sum with this two block diagrams, it will looks like x XOR y XOR z. So we have to keep that one in bracket, and finally we will get the output. So the difference between half adder and the full adder. So this is a simple difference. So half adder is a combinational logic circuit which adds two 1-bit digits. The half adder produces a sum of two inputs. We know already because this is the basic rule. So for if two inputs are there, we have to sum up with half adder. Previous carry is not used, so no previous carry. Here previous carry is used because of the carry is there in full adder. That is why we are using the previous carry. And here full adder is a combinational logic circuit that performs an addition operation on three 1-bit binary numbers. The full adder produces a sum of three input and carry value. So we know already three inputs we have to add with the help of full adder circuit. In half adder there are two input bits. We know already A, B. Here we are taking as an example. In full adder there are three input bits, that is we are taking as an example A, B, C. And here the application is sum is equal to A XOR B and carry is equal to A into B. Sum is equal to A XOR B XOR C in, and C out, that is carry output is A XOR B plus C input into A into B plus C input into A XOR B. So it says by taking the common values we will get this equation. It consists of one XOR gate and one AND gate. We know already, we already seen. And here it contains two XOR gates and two NAND gates, two AND gates and one OR gate. So with the help of realization of two half adders for one full adder, so this is the whatever the blocks we have to use. It is used in calculators, computers, digital measuring devices, etc. For full adder it is used in multiple bit addition, digital processes, etc. So for high end use we are using the full adder circuits. So up to now we discussed about the adders. So now half subtractor. So these are from now onwards we have to discuss about the subtractor concept. So for half adder, anyway we know that half subtractor, for subtraction part we require two inputs, that is two inputs we have to perform this subtraction. So half subtractor is a combinational circuit with two inputs and two outputs. So the difference and borrow is the output here, because we have to consider about no need to consider about sum and carry there. So here we have to use difference and borrow. Difference is nothing but we have to consider the difference between two inputs, and borrow is like we have to take the borrow from the others. So likewise we have to consider, because that is very essential for the subtraction part. So it produces the difference between the two binary bits at the input, and also produces an output borrow to indicate if A1 has been borrowed. In the subtraction A minus B, A is called as minuend bit and B is called as subtrahend bit. So we know this one, we call that one as that both inputs are one is minuend and next one is subtrahend. So we call that one as A and B, like that. So A and B are the inputs and difference borrow is the outputs here. So same as like as half adder. So A, B are the inputs here. So we have to subtract from one to one by other. Here we can remove 0 from 0, that is both are zeros. Here 1 from 0, sorry 0 from 1, so that means 1 is the what we call the difference, and the borrow is 0, and 1 from 1 we know that difference is 0 and the borrow is also 0. But the problem comes from this combination, that is 1 removed from 0. So that means we have to remove 1 from 0. So mostly this is impossible, but if possible, that is with only borrow. So if we take the borrow, so that means it looks like a 1 0. So 1 0 in decimal, this is looks like a 2. So now we can remove 1 from the 2. So that is why we can give the result, that is difference is 1. That is why difference is 1. Anyway, we are taking this borrow as a 1, right? So that is the borrow. So that is the 1 1. So this for particular 0 1 combination for half subtractor. So 1 1 is the that is difference, and borrow is the 1 1. So this is the simple concept. And for circuit diagram, this is the circuit diagram. So anyway, we have to represent this circuit with the K maps. We have to use the K map, then only we will get the circuit for this particular truth table. So we will get the XOR gate. If we observe both for adders and subtractors, only the XOR is the possible circuit for both the adders and subtractors. Anyway, it is producing correct accuracy value. And for this one, for borrow, so we are taking using that one AND gate with the help of one NOT gate for one input terminal, that is A. And for full subtractor, so it contains full means three inputs, and this last one we call that one as a borrow in, and we will take the output as a borrow and difference. So likewise we have to calculate. So it is a simple example. See, 0 minus 0, that is 0, difference is 0. So there is no problem, both are zeros, right? So 0 0. Here 0, this one is 0 minus 0, so the difference is 0 and the borrow is also 0. While coming to 0 with 1, so we have to compare that one 0 with 1. 0, that means 0 minus 1, that is both 1 1. So difference is 1 and the borrow is also 1. So here also 0 minus 1, that means difference is 1 and the borrow is also 1. So that is why we are using, because the third input is 0. And here 0 minus 1, so 1 1, both are 1 1, but the here again the 1 is there, that means difference 1 minus 1, that is 0. So that is why difference is 0, that borrow is 1. Here 1 minus, there is no problem, so we can directly use 1 0 here, because 1 minus 0 minus 0, so we can directly use. Here also 1 minus 0, the difference is 1, 1 minus 1, the difference is 0, and borrow is also 0. Here also there is no problem, 1 minus 1, that is difference is 0, and 0 with 0, difference is 0 and the borrow is also 0. Here 1 with 1, so 1 with 1 means, so difference is 0. Now 0 with 1, so 0 with 1, again we know that is both difference and borrow are the ones. So this is the only reason we are using this particular full subtractor for this particular block diagram, full subtractor truth table. So same full subtractor truth table. After getting the full subtractor table, we have to use the K map for both borrow and difference. So if you give this particular two tables for both K map tables for both difference and borrow, then you will get the equation, that is approximately for difference A XOR B XOR B input. And this is the block diagram, circuit diagram. So XOR gate with 3 inputs here, and AND here with 1 OR gate, and this is the combination. If you keep only one NOT gate here, then you will get the B output. That is the only difference between that adder and subtractor. So this is the circuit diagram for the full subtractor circuit with 2 half subtractors. So this is the simple circuit, again the same circuit, but only the inverter circuit is applied here. We know already only that inverter circuit is connected for only one input, then it will act as an subtractor for subtractor by the using of adder. And full subtractor, these are the applications of full subtractor. So full subtractors are also used in the ALU. We know already both are like one circuiter. We can realize with the help of one circuit for both adders and subtractors. That is why this is also used in arithmetic logic unit. also in computers. So full subtractors are extensively used to perform arithmetical operations like subtraction in electronic calculators. We know already for calculation part. Also these are used in microcontrollers for arithmetic subtraction. So subtraction for most of the time subtraction part we used these subtractors, full subtractors. For timers and program counters, as we know already, and full subtractors are used in processors to compute addresses tables. Same whatever we are using this application in the full adder circuit, the same full adder circuit we are applying. And also full subtractors are used in the DSP processors and networking based systems. Same whatever we are using that full adder circuits in the DSPs, the same full subtractor circuits also we are using. So this is a simple concept, ripple carry adder. So why we call this one as a ripple carry means, so here the carry is rippling here, rippling. That means from previous we are using only, so if it is one with one, so that one bit with one bit, so we will get the result. One bit with one bit with one bit, this we will get the result. That means this is a half adder, this is a full adder. But if we go for this multi bits, for 1 1 1 1 1 1 1 1, so definitely we will take this one as a, this one as a B. So let us consider 1 1 1 1 1 1 1 1. So this is a somewhat, this represents a 4 bit, we call this one as a 4 bit representation. This is also 4 bit representation. That means A and B are 4 bit representation here. Let us consider this one as a A0 B0, sorry, A0 A1 A2 A3. So likewise we have to consider here this one B0 B1 B2 B3. Likewise we have to discuss, and finally A0 with B0 we have to sum up here for first full adder, and whatever we are getting the sum we can directly take the sum, but while getting the carry we have to send this carry to the next level, that means second bit level. So this is again B1 A1 with B1, so 1 1 with 1 1, that means A1 with B1. So A1 with B1, and at the same time carry is also there, that is C0. So directly we can calculate the sum. Again we will take the S1 as the sum directly, but coming to that is whatever the carry from the second block, we take that one as a carry one. Again we are transferring this carry to the next level. So again B2 with A2, here A2 with B2, the same A2 with B2, and carry is also there. So we will add these three inputs. Finally we will get the sum. We will take this as usual, and finally we will get the carry and we will transfer this carry to the next level. So likewise we will continue from bit 1 to bit end. That means previously full adder circuits we are using for only single bit. Here this is for multi-bit operation. This is the combination of the circuits we will consider. So finally coming to the summary, combinational circuits and their internal circuits, like we already discussed about the adders, subtractors. Likewise, anyway, adders again half adder, full adder, and coming to subtractor, half subtractor and full subtractor. Also these are the basic building blocks for the whatever we are using that nowadays combinational circuits like encoders, decoders, multiplexer, demultiplexers and comparators. We will discuss, or we will use these circuits inside the block diagram for the particular major blocks like CPU, ALUs and digital processing units inside the whatever we are using the circuits. So this ends the today's discussion. Thank you.